Hello everyone and welcome back to our generative AI class. So today we are going to cover a hot new topic which is generative adversarial networks and they are known as GANs, okay? So GANs mainly market the, I would say, first great success of deep learning when it comes to generative AI. So in today's lecture, we are going to cover the in and out of this foundational like model paradigm, and we'll go through the following points. So first, maybe we will start with our motivation, like always, and then we are going to go through the architecture. So we will have an overview of the gas architecture. Then we will focus on the main like components of this architecture, the discriminator and the generator. After that, maybe we will focus on the training process, and we will go quickly through the math behind the loss function and details for the loss functions used in GAN. And after that, we will go through the convergence. We will see an example of the generative training before introducing few use cases, then, or I would say few examples of GAN architectures, okay? So to start with, I would like to show the transition, I would say, from previous lectures where we covered autoencoders and variational autoencoders to today's class where we are going to see GANs or generative adversarial networks. So the idea when it comes to autoencoders or variational autoencoders, let's say, so for VAEs, mainly we focus on density estimation. And if you remember, then the idea is that to learn latent variables that capture the essential structure of the data. So the idea here is that we produce a lower like dimensional representation, and what happens is that we generate samples from the latent space and from decoding. Okay, so now when we are moving or going to GANs, we have here a different approach. So instead of modeling the data distribution explicitly, they mainly rely on what we call adversarial computation. We will focus more on these, but let me tell you that there are like two components: the generator that tries to create realistic examples, and the discriminator that tries to distinguish real from fake images, let's say, or it depends on the use case. But today's class, we are going to focus on images, okay? So in this case, both networks try to improve through joint optimization, okay? And this is why this transition matters. So in VAEs, we have good structure. As you can see, we have like smooth latent space, but in use like usually, like you can see here, the output or what we get is mainly like blurred output. So this is what we maybe focused on in the previous lab, and with like different modifications we did, we can see how like the parameters can impact this output. Okay, so now when we have like a different structure and thanks to the generator and discriminator architecture, GANs are maybe kind of sharper. They have kind of high fidelity, the output high fidelity samples, and this is what we will see so far. Also, what I want to say that this competition, I would say, between the generator and discriminator networks in GANs, it's like it laid the foundation of today's powerful generative methods. Okay, so let's start with the architecture. And here, before diving into the details of this architecture, I want to mention that the goal of adversarial networks is to generate fake images. And the idea is that these fake images must not look like that they are fake. So the idea is that we are generating fake like images, but we want them at the same time to look realistic. And for this, like GAN can be broken down into the following components. We have the generator, like I mentioned before, the discriminator, and a very important component, which is the loss functions that we are going to focus on them today. Okay, so let's start with the architecture here. So what we have is this, like we have the generator, and the generator gets as input here random input noise. So the role of the generator here, like I mentioned, is to fool the discriminator, which is in the other side. And how it's going to fool the discriminator? It's by generating images as realistic as possible. Okay, so how this generator is going to generate images, it's going to get some random input noise, and then it is going to generate images. We will dive into the details of this later. Next, now what we have the discriminator, and the discriminator here, it takes as input the generated images by the generator, and also it takes some real images from our training data, let's say. Okay, and now once we have, like, for example, a generated image and a real image, the discriminator is now having the main idea, or the role of the discriminator in this case is to distinguish the generated images from the real ones. So if the discriminator is here having these two images, it is going to tell you, like, if this one, let's say, it's real, this one is fake, and going to take this kind of decision. So given an image, it's going to answer to the question fake or not. Okay, and then what we have is the loss. Okay, so we have the loss functions, which are, we don't have only one loss function. So mainly we have discriminator loss, and we also have generator loss. And the loss functions in this case are there to capture the I would say the problem as an optimization problem, and it will allow the model to learn. Okay, so the discriminator, it wants each of them, it has what I call conflicting goals. Okay, so at the time that the discriminator wants to become very good at distinguishing the real images from the fake ones, the generator now also wants to produce, or to generate, I would say, images that don't look like they are generated images. They look as realistic as possible. Okay, and the idea is again to fool the discriminator with the fake images. Okay, so this is the overall architecture, and this is how the generator is, I would say, connected to the discriminator, and at the same time, this is how we use the training data, and also a very important component, which is the random input noise, because this is our starting points when it comes to the generator. So don't worry, we're going to zoom on each maybe of these components and understand how it works in details. Let's focus with the discriminator. So the discriminator is just a simple classifier, okay? And the input data are real images and generated images and the labels here we have. So for example, if we have real image, in this case, the label for a real image is 1, okay? And if we have, for example, a generated image, so we have the label 0 for generated image, okay? So this is simple. If we have like true or false, or real or fake, so it means 1 or 0 as a label. So this is the main idea. And when it comes to the state of the art, for this simple network or simple classifier, I would say many networks has been employed. Let's say, for example, in 2014, the very first paper introducing generative adversarial networks by Jan Goodfellow. So the idea here is that they proposed a discriminator, which was as simple as a feed-forward networks. When I say feed-forward networks, we covered this so far, which is just a simple, fully connected network, okay? And then later in 2016, another paper was there where we introduced by Alec Radford and Luke Metz. So they produced what we call the cGANs. And it's a convolutional architecture that has been used in this particular paper. And it has, I would say, a discriminator architecture, which is very similar to the VGG 16 model, okay, or architecture. So we can use many architectures, and this is like I always teach whenever I teach my students deep learning. I say that so these are the main components. You have the fully connected, you have the different like dense layers there. You can have different type of layers like convolutional layers. You have pooling layers. You have like a plate, I would say, full of let's say puzzles, okay? And the idea is that you are going to select which part that you want to use. So for the discriminator, it's the same. We could use simple like neural networks. We can go for other examples. We can use like pre-trained model. We can use like convolutional layers. We can try to just I will show you later in the lab that we have layers, and we can just modify them, and we see each time the impact as like researchers or people who want to introduce new things. But for now, let's stick with the existing things, and we see how in these papers or in these research works how things were done. So this is mainly the architecture of discriminator that is composed, I would say, of a succession of like convolutional layers. Here we have, for example, here conv1, like then here conv2, conv3, conv4, conv5. So here we have 5 convolutional layers. Okay, for each layer now, the number of output channels like is, I would say, twice as big as the number of the input channel. Okay, and what we have as a final, I would say, unit or computational unit, here we have the sigmoid for binary classification, because like mainly in this example we have 2 classes. Okay, so this is an example of the architecture that could be used for a discriminator. Yes. So what we have now in terms of coding, let's say, of implementation. So this is a sequential model. This is a very important point that I want to insist or I want to mention. So sequential model means that if we have the output from this layer is the input to the next layer, and the output of this layer is the input for the next layer, and so on. And so we don't see kind of branches or things like this. So what we see is a sequential model, and so we try to just define. The first one is the conv2D layer, so we just call it from Keras, it's conv2D. And so we have here the kernel. It's size. It has the size of 3 channels we have, and filters. So we have 64 here. And what we use next is kind of like activation. So we use the Leaky ReLU, so with the kind of parameters which is here 0.2. So these things are hyperparameters, like I always mention, that we can fine tune or change, I would say. So for the second layer is the same, it's a conv layer, just we have different here parameters, 64 to 128, and here like the output from here that was 128 is going to come in here, and then we have 256 next again we have for the fourth layer, so it takes 256, and we have after that 500, sorry, 12, okay? And at the end, so each time we have, after the convolutional layer, the batch normalization and the activation. At the end, so we have the sigmoid just to have the final classification, because as you can see here, number one, so we have a binary classification, okay? So this is mainly the architecture of the discriminator. Now let's move to the generator. So the idea of the generator here, like we mentioned, that it takes kind of a random noise and outputs the image, okay? So the idea here, it's like architecture is very simple, I would say, and that of the discriminator mainly, but let's say we are building it, or we are as you can see here, it's in the opposite side. It performs, I would say, the opposite operation, okay? Same here, if we want to focus on the transposed convolution or operation that is used in this case, it has, for example, the half padding, no strides in this case, and it works like you can see in here, okay? So now let's maybe take a look on the code. And if I want to see the difference here, is that instead of using the convolutional operation, we are using the conv transpose 2D, which is the transpose of the convolutional operation, let me say. And in this case, we are moving from this a space towards the I would say the higher dimension space, okay? And just like in the previous case, we just have the 5 layers, and for each layer there is the conv transposed layer and batch normalization and then activation, okay? And at the end, so we find this tan, or hyperbolic tangent. So it's kind of in order to compute, okay, for the last layer, I would say, the activation function that we are employing at the last level, I would say. Now, let's see how we train these networks and how to train the whole architecture. So for this, we have different steps. We will start with the first one. So for the first step, like what we have the discriminator, and the discriminator is going to take kind of real data batch. So we are giving it a set of images and real images from our training data. And from this images, the discriminator is going to give us a kind of probability if the input image is real or not. And now what I want to mention in this case is that training a GAN is not an easy thing. Probably it could be tricky. And we can, I would say, iterate over the epochs and data batches. The idea is that the data needs to represent the distribution of images, and that you are trying to learn. And here are the this is mainly the first step. Now what we have is the code for this step before moving to step 2. So as simple as calling a function which is already defined in Keras that we TensorFlow, if you are using, called discriminator, and you're going to give it the real images from your data set. And so this is just a simple classifier that is going to return for you the probability of that image being real, okay? So the next step, now let's move on. The second step is we want the discriminator to become as good as possible. So we present we are going to present it the label, and we have, for example, real data. As label is real data, and corresponding to the real images, for example. And using the ground truth label and the probability predictions, we can compute the loss function in this case. So the idea is that this is one. It means that this image is real, okay? And this is a real data label. And we have the output from previous step. We are giving to the discriminator alongside with this information. And the idea is to accumulate the discriminator loss, okay? How to write this in terms of coding? So it's also very simple because we have the function compute discriminator loss, for example, and what we give as input to this function. So here you have two parameters. So the first one is the output in this case, and the second one is the label. Okay, you see them here. And no, so this is the loss. What will happen next is that gradient is equal to backpropagate loss. So just calling a backpropagate as a function, and you are giving it this like loss that we are defining so far. And now let's move on to step 3. And in step 3, maybe we focus on the generator side. So where we mainly, I would say, sample from random noises, from, let's say, a Gaussian distribution. And what we do is that we inject these into the generator. The idea is that we want to generate fake images, right? So the generator, once it's going to start from random noise, so it's going to generate kind of, I would say, random images, and it will have random generation, like generated images. Okay, so we generate as many fake images as we like have real images. Okay, so in this case, the output from the generator is going to be a set of images which are not real. These are fake images. Okay, so how to write this in terms of code? So again, we have like, what is this random noise? So random noise is just a length of real images. So we are like for let's say we have 10 images real, then we are going to generate 10 like random noises. Okay, and then we are going from this to generate to give this random noise, which is Gaussian, to the generator. So the generator in this case is going to give you as output the fake images. Okay, so simply we define the random noise. Okay, we need as random noise as we have images, and then these what we define the fake images, which are the output from the generator. Then so just we call the generator with giving the random noise we are defining so far. Okay, as simple as this. So now step number 4. So in the first step, what we do is that, again, now we pass these images through the discriminator in order to estimate like the probability of these to be real, and also we provide the the network with fake data label to like continue computing the discriminator loss function. This is how it works. Okay, so now, so this is coming from previous steps. We have that many images, given them to the discriminator. We assess the generated images with the discriminator and get the probability of them being real. This probability, along with the fake data label, is given as input to the discriminator loss. Okay. And in terms of code now, how to just code this. So the idea is that output is equal to that. What we are going to call is, we are going to call the function discriminator. We are giving the discriminator as input the generated images. We call them fake images, and then it's going to give us the output. Okay, this output is going to be mainly useful for computing the loss. So here we have the function compute discriminator loss, which is corresponding to this like point, and it takes the output. Also, it takes the labels equal to 0, and like this is giving you the loss. This loss then is going to be given to the back propagation, and each time we keep incrementing. So the gradient is equal to the previous gradient plus the back propagate, given this loss. Okay. The next step now, which is the 5th step, it's like we want to compute the discriminator loss in this case. So the discriminator loss function, we are going to compute for a full batch, which means that we can propagate through the gradient, for example, and we are going to update each time the parameters of the discriminator. Okay, but propagate, we have the discriminator loss. We're going to back propagate gradient of the loss with the gradient descent, and then we are going to like update the parameters of the discriminator and so on. Okay, so it's kind of a loop. Now, in terms of code, just we are going to update discriminator given or taking into account the gradients. So now step number 6 is mainly where like we now need to compute the generator loss function. Okay, so how it works, like the idea is that we can reuse the previously generated fake images. Okay, so these images we already had them. We are going to use them and and get the estimated probability for each time for a newly updated discriminator. Okay, because we want to fool the discriminator, so we provide now the real data. Okay, and we give the real data label, which is equal to 1 to the model. Okay, and using the probability estimates and the ground truth labels, we can compute the I would say the generator loss. Okay, so we are going to consider all these points in terms of code. Now, how to write this? We have the discriminator is going to take for sure the fake images, and we save that as output. Next, the loss. Now the loss is like we call compute generator loss in this case, and we give it the let me say the label equal to 1 for the 1 second please. Okay, here we have the label is equal to 1 and the output, which means that the real label and the output, and then we do the back propagation and back propagate the loss. It's a gradient. Now, step number 7 is with the computed loss. What we do, we just need to backpropagate the loss, like gradient, and update the parameters of the generator. So we keep like we backpropagate and we update the parameters of like this component of generator. And in terms of code, just as simple as writing update generator gradient. So here what I'm showing you is pseudo code. So we are seeing, given the different like illustrations, how to write these different steps in terms of code. Now the idea again is that this is going to happen for like real images in batches, and it's also going to happen for epochs, for epoch in epochs. Okay, so for all the epochs and for all the batches, we are going to go from step 1 to step 7, and this is mainly the pseudocode. Okay, the pseudocode is kind of like the algorithm and how things works. Otherwise, when it comes to the implementation, you will see now we will implement an advanced like example. But before moving to that, let's complete because what we've seen so far is the architecture, like the discriminator, like the generator, like the different steps for training the GAN model, but we didn't mainly focus or zoom in the loss function. This is what we will do now. So we will see 2 loss functions. So we start with the discriminator loss first. Okay, so as we mentioned previously, that the discriminator is a classifier, and for the classifier, what we are going to use, we are going to use the cross-entropy as a optimization function. So in general, what we want to minimize is the following. Okay, so this like one real or one fake here is an indicator function, which is equal to 1 if the image is real. So 1 real is equal to 1 if it's real. So we are going only to consider the log of d of images. Okay, take it easy, just where I'm making this as simple as possible. Okay, so here this is going to be ignored if this is real. Okay, this is going to be ignored, the number 1 I mean, if this is equal, this is fake. Okay, otherwise, so if not, then it's going to be equal to 0. What is this d images that we are using here, for example? So this is the probability that the image is real as inferred by the discriminator. Okay, because here we have the letter D, means the discriminator is telling you that this image is real. Now this is the probability that it's real. Now if we want the opposite, we want the probability that it's fake, so it's the opposite. So it's 1 minus the probability that it is real. Okay, so this is the idea, and this is what we need to minimize. So we need to minimize this function. Okay, and in the case of that the image is real, now the loss function per image simplifies to just we have minus log this from where the minus is coming, by the way, and just this we are ignoring log like d of images, and this part is equal, let's say, to 0. Okay, otherwise in the other case where the image is fake, so the loss function per image simplified to the minus log of 1 minus d of the image, which is the the generated random noise. Okay, and so the generated random noise here is the image generated by the generator. And to learn now the parameters of beta, the discriminator, just we simplify that by this rule. Okay, so it's the same one. So sorry, this is for the discriminator loss for now. So the idea is that, again, we have the in the case of like the discriminator, we need to minimize the LD. So the idea is that we want to fool the discriminator, and the generator needs to minimize that element. So to maximize it, what we do, we want that the random noise here in this case to look similar as possible to one real here, and to do so we will have the generator to minimize the following function. Again, we learn to like the parameter theta here of the generator, and we run the gradient descent algorithm. Okay, just we are running the gradient descent and updating here or learning the parameters. Okay, so how it works next, that we have the convergence of the generative training, which means that a discriminative process is typically what is learned in a supervised learning setting. Like, for example, if you have, I would say, x is like an input variable and y is a target variable. What we want is we want to learn the probability of x given y, and this is what we did all the time. So we learned the distribution of the variable y conditioned by x, okay, on x. In the case now of generative process, we want to learn something else. So what we want to learn is x and, okay, y. So in the context of GANs, this is what we do. We want to learn the distribution of the real images. So if, for example, here, P real is the distribution of real images, and we have also the P generator is the distribution of the learned, the distribution which is learned by the generator. So we want to the training to converge, such as we have P real is equal to P generator, to P of generator, which means that we want that we don't distinguish real from generated images. And the idea here is that what happens is this mainly happens when it converges after multiple steps. It converges. For example, here what we have, the discriminator loss function is minimized when we have this d of images is equal to probability of real image is divided by real image plus the sum of both of them, like the real distribution or generated distribution. Okay, and therefore now whenever we have them equal, the idea is that the image is equal to 1 divided by 2, which means that, let's say, half. Okay, so meaning that the discriminator has no idea if the image is real or fake. Now means if we have our objective is that we want at the end that the d of image is equal to 1 divided by 2 or a half. Okay, so the training in this case converges when the discriminator reaches a very low level of confidence in prediction. Now I'm going to illustrate what I'm saying. So if you didn't understand that much, don't worry. Things are here. I'm here to make things as clear as I can. So for this reason, I made this illustration for you. Now, what you have you have here, these are the real images. Let's say that our data set has these real images, and we have these are real, and from the other side we have these images that are fake. In the start, the probabilities that are between 0 and 1, no, the probability value cannot exceed 1, cannot be negative. So probability is between 0 and 1. And in order to not distinguish between these like fake and real images, the idea is to have the probability equal to a half, okay? We want to have these probability values come in here, so to make sure that these are there is no difference, I would say, between the real and generated images. So now what we'll do is that imagine all your real data images, like the images we can see on the left. We are having them in there, okay? Next, now the generator is going to start by producing completely noisy images, like these images you see over here, okay? And with the points in this case are representing the probabilities of this, I would say, like line to like if for example they don't look like the real data at all, for example for this one and this one, they look, I would say, like the real data. So the discriminator, if for example we have that it don't look like the real data in this case, the discriminator then is going to look at two sets of points, and the real ones and the fake ones, both of them, okay? So it's going to consider both of them, and the job of the discriminator in this case is to learn to assign, I would say, high probability to the real data and the low probability to the fake data. So this is how it will work. If you can see now, probability values are going to change. So at first the discriminator trains and become very good at separating real from fake data. Okay, so this you focus with the data here, it's like changing, and this is why we are here. There is a clear distinction between real and fake data. Once that happens, now what will happen? The generator is going to update itself. It observes where the real data lie and starts shifting its fake data closer to that region, like for example like this. Then the discriminator trains again on new fake points and tries to separate them from real ones. The generator is going to respond by moving its outputs even closer, okay? And so this back and forth continues until the generator fake data, I would say, almost overlap perfectly with the in this case real data, and the point at that point, let's say, the discriminator can no longer reliably tell them apart. So this dynamic, the generator improving to fool the discriminator, and the discriminator improving to detect the generator, is the core institution behind how GANs they learn, okay? So this mainly, like here we have the final results, which are, we cannot distinguish between them. This is why we have the points at this point, like of 1 divided by 2 or a half. So this illustrates how GANs learn from pure noise to a fully believable image. And here in this case, I can tell you that a vanilla GAN cannot control what it generates. So this can maybe take us to the next topic. But before that, let me quickly come back through these slides. What I want to focus now with is focus with these points. I'm going to play them quickly, and with the changes happening like in the fake data, okay? See, so the more it converges, okay, then it shows you like probably we cannot distinguish between these two, okay? And now here, it's generating images, okay? But is it possible now to make some conditions, let's say, on the generated images? Like, for example, I want to say that generate the image with like of this man in a given position, for example, or I say I want like the flag is red color in every image, for example, or I would say I need like a specific thing. So this cannot happen in this like kind of vanilla GAN. However, it is possible in other architectures. This probably is taking me to the next point, where I want just to highlight, like I would say, few architectures that I am selecting for you. The first one is the vanilla one, which only based on like where it's just a game, I would say, between two networks, the generator and the discriminator, and that produces the fake samples. This generator is going to generate, I would say, produce fake samples, and the discriminator is going to judge each time like these samples. And through this adversarial game, the generator learns how to synthesize the data. So now the generator gradually improve the, I would say, the discriminator become harder to fool, let me say, and the adversarial process faces like forces high quality generation, which is the case that we've seen so far. Next, we have different like types. We have beyond like the vanilla GAN, we have the CycleGAN. It's an amazing architecture that we are going to explore right now. And the idea in here is that we translate an image A to B without paired data, okay? So in this case, I will show you an amazing example. And after that, sorry, we're going to move the conditional GANs. Mainly, if you consider that in terms of, I would say, time, the conditional GANs that came first, but I'm keeping to the end because we will focus on them for the implementation. And this one, just we're going to go through, I will show you the example. And next, when we will cover the style transfer, maybe we will see things like similar things or context, I would say. Now, the idea behind conditional GANs, like I mentioned, is that there is kind of a control. They also are known sometimes in their notation. It's cGANs, so it's a little c in here. So they write it like this. cGAN. So the C is from conditional and generative adversarial networks for GANs. And the idea is that we control this generation. Like I say, if I want, for example, a red color, or I want a specific thing on condition, so that is going to be covered for the cGANs. Okay. Now let's go through the CycleGAN. And the idea is that now that we understand how GANs work, we can move, okay? Because this is mainly something that is more advanced. And the idea is then when we deal with images, we are often interested in changing the visual style. Like, for example, transforming a horse into a zebra. And what's amazing in that is that we can do this without needing paired images, what I mean like by paired images, that I don't need matching examples such as pictures, or like I don't need the same picture of a horse, like of the same horse, and another in the exact like that exact same horse as zebra. So in this case, we say that these one-to-one pair don't exist because in the real life. So, and also collecting them would be impossible, let me say. So instead, a CycleGAN, in this case, learn the mapping using only two separate collections of images, a set of horse images, okay, and another set of zebra images. And with no correspondences between both of them, this is exactly what CycleGAN allows us to do. Unpaired image-to-image translation, right? So the idea is that they achieve this using clever cyclic loss, and that, like you can see it here, like what is happening like in this one. So we have, let's say, two generator discriminator pairs, one for each domain, ensuring that if you translate an image to other domain, let me say, and then, for example, go back, you recover something close to the original one. And this is in this example, like the CycleGAN was trained, let's say, on two sets of natural images, horses and zebra, but without any one-to-one matching between them yet. So it learns how to transform a horse into a zebra and vice versa. Okay, it can happen that from zebra to horse as well. So this is essentially a form of style transfer, right? And so the way like CycleGANs do this is by using a cyclic loss. So instead of having just one generator and one discriminator, CycleGANs use two generators and two discriminators. This is interesting. For these, like we have one for each domain, and the key idea mainly is like the cycle consistency, which means if you transform an image from domain A to B and then bring let's back from let's say to A, you should recover the original image. That relationship between the two domains is what makes like unpaired translation possible. So this is cool, right? And this is mainly some of the clear capacities or great things that GANs or this particular type CycleGANs can do. I would say it really rocks when it comes to style transformation. Okay, now just an example. Now let's move to the next example. I will not take lots of time because I will give it more time next time in the next video. So another interesting architecture is or type of GANs is the cGANs or conditional GANs. And so far with regular GAN, we can generate data purely from random noise, right? And it works. But we have no control, as I mentioned, over what gets generated. Like, for example, if I train MNIST dataset, the model may generate any digit between 0 and 9. I have no control, something like I want to say, or I cannot like tell to the model, please, let's say, generate 1 instead of 7, or I force the model to generate number 6, or I say, hey there, just I need 4, like generate number 4. So this is not possible with the vanilla, I would say, GANs. However, it is with conditional GANs. So conditional GANs fixes this, and this is what we will be covering in lab 3. Okay, so thank you so much. If you have any questions, please never hesitate to contact me. And in the next video, I will like maybe focus more on the lab. Thank you.